Hi, I'm Rochelle Crosbie Watson, and today we're going to talk about how to characterize the force properties of skeletal muscle so that we can apply that to our various animal models of muscular dystrophy and evaluate whether the treatments that we're using in these mouse models are really efficacious. So we're going to use many different outcome measures, and some of them are listed here. We're going to look at grip strength. We're going to look at how grip strength can be used to look at a fatigue-like property. We're going to look at wire hang tests. We'll also look at muscle twitch characteristics and specific force properties, as well as an ex vivo force measurement. So many of these tests can be done to really evaluate the effect of a treatment on skeletal muscle, and they can reveal different properties of skeletal muscle that are affected by certain treatments. So these tests are really, really valuable. Let's talk about the grip strength analysis. What's really great about grip strength is that it is a non-invasive measure of muscle force. So what you're looking at here is a force transducer, which basically is attached to a little bar that can be used by the mouse. In this case, we're going to be talking entirely about outcome measures for murine models of muscular dystrophy. So you can see that the setup is here. The mouse is pulling on a bar. We're going to take a closer look at that bar in a moment. And that bar is connected to a force transducer, which measures the force on which the mouse is pulling the bar. So let's take a little closer look. You can see the mouse is pulling on the bar. That bar is connected to a force transducer. So here's the mouse close up pulling on the bar. The experimenter is holding onto the tail with his or her hand. So this is really like an air pull-up, if you will. This is a really strenuous test for a mouse or for a human to do. So that's what we like to show you in this close-up picture. This is a really strenuous test. The mouse is gripping onto the bar with its forelimbs. So we can get a lot of information from the grip strength analysis. We can get information about maximum strength, and we can also get information about fatigue-like properties. So we're showing you below another setup in which the mouse is pulling on a grid instead of on a bar. Again, the grid is connected to a force transducer. So from this information, we can really get a maximum strength from the pull that the mouse is generating on the force transducer. By taking that strength and dividing it by the body weight, we can get specific force information. So that's force relative to body weight. We can also conduct experiments where the mice pull on the bar in 5 closely separated trials. And what you can see, and we're going to see it in the next slide, is that the mice that have muscular dystrophy actually fatigue over time and aren't able to pull with as great of strength at trial number 5 compared to trial number 1. Before we look at that data, let me remind you of the various types of muscle contraction. And this does become somewhat important when we're thinking about how to test skeletal muscle. Remember that muscles in the body have different functions, and that some muscles in the MDX mouse, or the mouse model for Duchenne muscular dystrophy, are much more susceptible to contraction-induced injury. So for instance, the diaphragm muscle is very susceptible to injury in the MDX mice. So oftentimes we may look to the diaphragm as sort of our worst case scenario. Remember that skeletal muscle contraction can be isometric or isotonic, and the distinction between the two is whether there is a length change during the skeletal muscle activity or during the contraction. There is also concentric and eccentric contractions. Let's illustrate them in the next slides. So during an isometric contraction, there is no change in length. An example of that would be trying to lift a very, very heavy table where you're contracting the skeletal muscles, but there is actually no change in the overall length of the skeletal muscle itself. The other is a concentric contraction where there is a decrease in length, and an eccentric contraction where there is an increase in length. So setting down a heavy weight is an example of an eccentric contraction. And scientists have demonstrated that these eccentric contractions are quite damaging to skeletal muscle. And in particular, in dystrophic muscle, the eccentric contraction is very damaging and really allows us to probe the effects of a treatment or a gene on the ability of that treatment to restore skeletal muscle membrane integrity and force properties. So that grip strength analysis that I was telling you about. What we're looking at here on the y-axis is the grip strength relative to maximum. So in other words, the animals were analyzed during 5 separate trials, and the data was normalized to the maximum pull that a mouse gave on the first trial, okay? And wild-type mice were used as the control in these experiments. And you can see that wild-type mice don't really drop their grip strength properties over these 5 separate trials, but dystrophic MDX mice dramatically drop their grip strength profile over the 5 different trials. I also want to point out, and what's not shown here, is that the maximum grip strength properties of the MDX mice, which occur during that first trial, are much lower than the maximum grip force properties of a wild-type mouse, which is not really shown to you here. So what you can get from this is some information about the fatigability, if you will, of the MDX mouse relative to wild-type. And you can plot this data in a number of different ways. You can plot it as we've done here, showing you the decline in grip strength as a series of these 5 different trials. We could also plot it as the difference in grip strength from trial 1 to trial 5, or we could also just show you the data from trial 5. And there's a large difference between wild-type and MDX, which means that we'll be able to discern a difference if we're coming in with interventional treatments. Do we see improvements in the MDX profile? So, another non-invasive test is the wire hang test. What I love about this test is that it's really low tech. So in this experiment, you have a wire, or in this case, the top of a cage, that's suspended over really a trash can. Honestly, you can do these experiments with the wire over a trash can. The trash can is lined with pillows. And the mice are attached to the wire, or in this case, the cage top, and they want to hang on. It's very similar to doing a chin-up. The mice don't want to fall below, although they're very much protected and cushioned when they do fall. So the test is just to see how long are they able to do this chin-up. Here's a mouse on the wire hang test. And what you'll see if you look at the amount of time that the animals are able to hang on, that the wild-type mice are able to hang on in this wire hang test for much, much, much longer than the MDX mice. And so we're able to get these very distinct differences between wild-type and MDX in their ability to hang on to the wire during the wire hang test. Again, it's a non-invasive method of surveying skeletal muscle strength. So, other measurements, if we really want to get at the specific properties of a given isolated muscle, let's say you're really interested in the EDL muscle or the TA, the soleus, or even the diaphragm, those muscles can be isolated from the animal and can be analyzed for the different twitch characteristics. So that's a single given electrical stimulation followed by tension that develops after the stimulation. And we can also look at tetanus, which are multiple action potentials, multiple stimulations given to an isolated muscle. And we can calculate specific force properties as well from these various experiments. So you've seen this setup before, in which the skeletal muscle is isolated and attached to a force transducer. The skeletal muscle length is adjusted at the start of the experiment, and then the muscle is stimulated electrically to contract. The twitch, which results from that electrical stimulation, is shown here. What you're looking at is the twitch characteristics or the twitch profile for wild-type mice, MDX, and MDX eutrophin deficient. Now remember that mice that are dystrophin deficient and eutrophin deficient are a very severe model of muscular dystrophy. They lack that compensatory expression of eutrophin which takes place in the MDX. So think of these as double knockout mice that are very, very severe. So we've got normal mice, dystrophic mice, and very, very severe dystrophic mice that are shown to you here. So you can see that there are some differences in the peak tension that's able to be generated by the skeletal muscles that are isolated from these 3 different mouse models. So from these experiments, we can get some important information about the twitch characteristics of isolated muscle, including information about peak tension or the maximum force generating capacity of skeletal muscle. We can get information about the relaxation time. Remember that the pumping of calcium back into the sarcoplasmic reticulum is the action that allows skeletal muscle to relax. We can look at latency, which is the time from stimulus to contraction, and we can also look at fatigue characteristics. So, remember that mice are active creatures, and they're actually very active at night. They're nocturnal. So we can ask all kinds of questions layered upon the specific force question. For instance, do we see differences in sedentary versus active MDX mice? So as an example of an experimental approach to address questions related to activity, scientists took MDX mice and allowed some of them to remain sedentary and some of them to have access to a voluntary wheel. Now, these types of experiments are quite important to remember because our long-term goal is to apply this information to the human DMD population. Do we advise boys with Duchenne to exercise, or do we advise them to be much more cautious with their exercise? And if we do advise exercise, what kind of exercise would benefit them the most? So these types of experiments are done to really investigate the effects of sedentary profile and the effect of exercise on the dystrophic outcomes with the long-term goal of advising patients. So we can apply these two different regimes to mice and then look at the muscle strength characteristics after they've undergone these two different treatments. And what we see is that the mice that were undergoing the active treatment, the running mice, had very different characteristics for multiple muscle groups, including the diaphragm, the EDL, and the soleus. These animals experienced much less ability to continue to perform and demonstrate the tension that the sedentary mouse was able to develop. So these experiments are showing us that for some muscle groups, particularly the diaphragm muscle, is damaged by the extensive activity on the exercise wheel. But other muscle groups, like the EDL and the soleus, experienced less damage from the activity profile. On top of that, scientists have been looking at different types of skeletal muscle contractions. Remember, we investigated and talked about how eccentric contractions were particularly damaging to dystrophic muscle. Scientists have also looked at isometric contractions. So the skeletal muscle length is altered at the outset of the contraction. And I hope that you can see from this profile that MDX mice and wild-type mice can differ significantly at the longer lengths of skeletal muscle at the outset of the isometric contraction. In addition, muscle undergoes repeated use. And so scientists really want to look at the effect of repeated use on skeletal muscle function. So this slide is showing you the in vivo force generation properties of the gastroc muscle after 20 trials. So you can see that in wild-type mice, even after 20 trials, the force-generating profile is very, very similar to the first trial. But in MDX mice, they perform much, much more poorly during the 20th trial compared to their performance at the first trial. Finally, we've discussed how eccentric contractions are particularly damaging, and this is really illustrated in the plot here. If we look at the number of trials of eccentric contractions, we can see that there's a slight drop in force production for wild-type animals. But that drop in force production is even more pronounced during eccentric contractions from the MDX mice. These are, again, performed on isolated skeletal muscles. So really that eccentric contraction protocol really damages the skeletal muscle, and particularly the dystrophic skeletal muscle is very susceptible to that damage, and we can very easily see that. And this would be a great experiment with which to take a mouse that's undergone a treatment and ask, did that treatment improve the performance in drop in force for eccentric contractions? So we've also looked at the tension reduced in previously stimulated muscle for MDX mice, and we can see that that tension is dramatically reduced in the eccentric contractions. So this is just another way to analyze the data that was shown to us on the previous slide. You can really see that the MDX mice are very sensitive to eccentric contraction protocols. So here's a 1-minute write. Choose 2 methods to evaluate force properties in dystrophic mice and explain the potential problems of using these methods. Each method has its pros and cons. Think about the advantages and disadvantages of each method. So, I hope today you've learned that there are many different methods, both invasive and non-invasive, that we can use to evaluate the force properties of skeletal muscle, particularly within the context of muscular dystrophy. One of the questions that you have to think about is, do we need to change force properties in order to have a successful treatment to skeletal muscle? Or is the goal simply to improve the survivability of muscle? These are things that are actively debated in the field and something that you can think about too.